When a UPS is energized, the transformer within it draws a large magnetizing current to establish the magnetic field. This current can be substantial, potentially reaching up to 10 times the full load current of the transformer. However, it typically decays rapidly to a very low level, often below 1% of full load. If the UPS includes a large capacitor bank, it may draw a significant charging current upon energization. Similar to the magnetizing current, this charging current also decays rapidly, especially if the capacitors are connected in series with resistors. The rectifier diodes within the UPS can also contribute to a large inrush current when the unit is turned on. This current is typically limited by the impedance of the transformer and the filter inductors in the system. UPS have the potential to generate harmonic currents, which are multiples of the fundamental frequency of 60 Hz. These harmonics can circulate through the electrical system and lead to inaccurate readings on analog meters. Based on measurements taken using an RMS foot meter that match readings on the switchboard meter, it suggests that the analog meter is not significantly affected by harmonics. The difference between the no-load current measured at the UPS and the main switchboard could be attributed to the transient nature of the magnetizing and charging currents. These currents may only be present for a fraction of a second and therefore not fully captured by the analog meter. It's possible that the observed inrush current on the switchboard meter is primarily due to the magnetizing current of the transformer feeding the switchboard, rather than the UPS itself. To investigate further, firstly consult with the UPS manufacturer for a more detailed analysis and explanation of the no-load current characteristics of the specific UPS model. Secondly, use digital metering equipment, such as a power analyzer, to capture and analyze the current waveform. This will help identify the specific components contributing to the no-load current, such as magnetizing current and harmonic currents. Thirdly, monitor the UPS no-load current over time to ensure that it remains within acceptable limits, as specified by the manufacturer. Transformer magnetizing current is a significant factor to consider. When a transformer is first energized, it requires a substantial current to establish the magnetic field in its core. This inrush current, also known as magnetizing inrush, can be several times higher than the transformer's rated current. The magnitude and duration of the inrush current depend on several factors, including the transformer's size, design, and the point on the voltage waveform at which it is energized. Capacitor charging current is also important. UPS systems often incorporate large capacitor banks to provide filtering and energy storage. When the UPS is turned on, these capacitors need to be charged, which results in a transient inrush current. The magnitude of this current depends on the capacitance value and the charging circuit impedance. Rectifier inrush current must also be addressed. The rectifier stage in a UPS converts alternating current to direct current. When the rectifier is initially energized, the diodes conduct heavily, drawing a large inrush current. This current is limited by the impedance of the transformer and any filter inductors in the circuit. Finally, harmonic currents must be examined. UPS systems can generate harmonic currents due to the nonlinear nature of their components. These harmonic currents can distort the voltage waveform and interfere with other equipment connected to the power system. It is essential to analyze the harmonic content of the current and voltage to identify and mitigate any potential problems. To accurately assess the no-load current and its components, digital metering equipment is recommended. A power analyzer can capture and display the current and voltage waveforms, allowing for detailed analysis of the harmonic content and transient events. This information can help identify the source of the high no-load current and determine the appropriate corrective actions. To mitigate the effects of inrush currents, several techniques can be employed. Firstly, using soft-start circuits can gradually increase the voltage applied to the transformer or capacitors, reducing the magnitude of the inrush current. Secondly, adding series impedance such as inductors or resistors can limit the peak inrush current. Thirdly, employing controlled switching techniques can energize the transformer at a point in the voltage waveform that minimizes the inrush current. To address harmonic currents, several mitigation methods are available. Firstly, using harmonic filters can block or reduce the flow of harmonic currents. Secondly, employing active harmonic correction can inject currents that cancel out the harmonic current. Thirdly, specifying equipment with low harmonic distortion can minimize the generation of harmonic currents in the first place. It's important to consult with the UPS manufacturer for specific recommendations on inrush current and harmonic mitigation techniques for the particular UPS model. The manufacturer can provide valuable insights into the UPS design and performance characteristics. Regularly monitoring the UPS no-load current is essential to ensure its proper operation. By tracking the no-load current over time, any significant changes or trends can be identified, which may indicate a potential problem. Analyzing the current waveform is also important to identify any abnormal conditions, such as excessive harmonic distortion or transient events. Proper grounding is crucial for minimizing the impact of harmonic currents and ensuring the safe operation of the UPS system. A well-designed grounding system provides a low-impedance path for fault currents and helps to reduce voltage distortion. It is essential to verify that the grounding system meets applicable standards and regulations. In addition to addressing the no-load current issue, it is also important to consider the overall power quality of the electrical system. Voltage sags, swells, and transients can affect the performance and reliability of the UPS and other sensitive equipment. Power conditioning equipment, such as surge suppressors and voltage regulators, can help to improve power quality and protect against these disturbances. Power quality monitoring can help identify potential problems and ensure that the power system is operating within acceptable limits. Consider a scenario where the UPS is feeding a critical load, such as a data center. In this case, any disruption to the power supply could have significant consequences. Therefore, it is essential to take proactive steps to ensure the UPS reliability and performance. This includes regular maintenance, testing, and monitoring. Proper ventilation is crucial for preventing overheating and ensuring the long-term reliability of the UPS. The UPS should be installed in a well-ventilated area with adequate airflow. The temperature should be maintained within the manufacturer's recommended range. Overheating can cause premature failure of components and reduce the UPS lifespan. Regular inspection of the UPS components is essential for identifying any potential problems. This includes checking the batteries, capacitors, fans, and other critical components. Any signs of damage, corrosion, or wear should be addressed promptly. Replacing worn or damaged components can prevent more serious problems and extend the UPS lifespan. Battery testing is crucial for ensuring the UPS ability to provide backup power during a power outage. Batteries should be tested regularly to verify their capacity and performance. Weak or failing batteries should be replaced immediately. A comprehensive battery management system can help to monitor battery health and provide alerts when maintenance is required. In addition to addressing the technical aspects of the no-load current issue, it is also important to consider the economic implications. A high no-load current can result in increased energy consumption and higher electricity bills. By reducing the no-load current, energy savings can be achieved. In some cases, the cost of implementing mitigation techniques can be offset by the energy savings. Consider also the potential impact on the environment. Reducing energy consumption helps to conserve natural resources and reduce greenhouse gas emissions. By addressing the no-load current issue, a positive contribution can be made to environmental sustainability. Proper documentation is essential for tracking the UPS performance and maintenance history. All measurements, tests, and repairs should be documented. This documentation can be used to identify trends, diagnose problems, and plan future maintenance activities. A well-maintained documentation system can help to ensure the long-term reliability of the UPS. Training is also essential for ensuring that personnel are qualified to operate and maintain the UPS system. Training should cover the UPS operation, maintenance procedures, and troubleshooting techniques. Properly trained personnel can help to prevent problems and respond effectively to emergencies. The National Electrical Code, or NEC, provides guidance on the safe installation and operation of electrical equipment, including UPS systems. It is essential to comply with all applicable NEC requirements. For example, NEC Article 480 covers the installation of storage batteries, which are commonly used in UPS systems. NEC Table 310.15b16 provides ampacity ratings for conductors. It's also important to be aware of industry best practices for UPS installation and maintenance. These best practices can help to ensure the reliability and safety of the UPS system. The Institute of Electrical and Electronics Engineers, or IEE, publishes standards and guides related to power systems, including UPS systems. These standards can provide valuable guidance on design, installation, and maintenance. For example, IEE Standard 1564 provides recommendations for battery management in UPS systems. Consider the potential impact of the UPS on the overall electrical system. The UPS can affect the voltage stability, harmonic distortion, and power factor of the system. It is important to coordinate the UPS installation with the utility company and other stakeholders to ensure that the system operates properly. In summary, addressing the high no-load current in a UPS system requires a comprehensive approach that includes analyzing the current waveform, identifying the contributing factors, implementing mitigation techniques, monitoring the UPS performance, and following industry best practices. By taking these steps, the reliability, efficiency, and safety of the UPS system can be improved. Also consider the possibility of using a more energy-efficient UPS. Modern UPS systems are designed to minimize energy losses and improve overall efficiency. Replacing an older, less efficient UPS with a newer model can result in significant energy savings. It is also important to consider the load profile of the UPS. The UPS should be sized appropriately for the load it is serving. An oversized UPS can result in increased energy losses and higher operating costs. In some cases, it may be possible to reduce the size of the UPS without compromising reliability. Consider the potential for using renewable energy sources to power the UPS. Solar panels, wind turbines, and other renewable energy sources can provide a clean and sustainable source of power. Using renewable energy can help to reduce the environmental impact of the UPS system and lower operating costs. Also consider the potential for using energy storage systems in conjunction with the UPS. Energy storage systems, such as batteries or flywheels, can store energy during off-peak hours and release it during peak hours. This can help to reduce the demand on the grid and lower energy costs. Evaluate the potential for using demand response programs. Demand response programs allow customers to reduce their energy consumption during peak demand periods in exchange for financial incentives. Participating in demand response programs can help to lower energy costs and improve grid reliability. Consider the potential for using smart grid technologies. Smart grid technologies enable real-time monitoring and control of the electrical system. These technologies can help to optimize the operation of the UPS system and improve overall grid efficiency. Regularly review the UPS configuration and settings. The UPS should be configured to operate in the most efficient mode possible. Unnecessary features or settings should be disabled. Regularly update the UPS firmware and software. Software updates often include improvements to efficiency and performance. It is important to keep the UPS up to date with the latest software releases. Maintain a regular cleaning schedule for the UPS. Dust and dirt can accumulate on the UPS components, reducing its efficiency and increasing the risk of overheating. Regularly cleaning the UPS can help to improve its performance and extend its lifespan. Consider the potential for using remote monitoring and control systems. Remote monitoring and control systems allow personnel to monitor the UPS performance and make adjustments remotely. This can help to improve efficiency and reduce the need for on-site visits. By taking these steps, the efficiency, reliability, and sustainability of the UPS system can be further improved. Proper labeling of the UPS and associated equipment is essential for safety and maintenance purposes. All cables, connections, and components should be clearly labeled. The labels should be durable and resistant to environmental conditions. Also maintain an up-to-date set of drawings and diagrams for the UPS system. The drawings should show the electrical connections, grounding system, and other important details. The drawings should be kept in a safe and accessible location. Consider the potential for using surge protection devices to protect the UPS from voltage transients. Surge protection devices can help to prevent damage to the UPS and other equipment connected to the power system. Regularly inspect the surge protection devices to ensure that they are functioning properly. Maintain a stock of spare parts for the UPS. This will allow for quick repairs in the event of a failure. The spare part should be stored in a clean and dry location. Consider the potential for using uninterruptible power supplies for other critical loads. In addition to protecting the main UPS system, it may be necessary to protect other critical loads with their own UPS systems. This can help to ensure that all critical loads remain operational during a power outage. Regularly test the UPS system under load. This will help to verify that the UPS is capable of providing the required power during a power outage. The load test should be performed according to the manufacturer's recommendations. Document the results of the load test. Consider the potential for using a redundant UPS system. A redundant UPS system consists of two or more UPS units connected in parallel. If one UPS unit fails, the other units can automatically take over the load. This can help to ensure that the critical loads remain operational during a UPS failure. Implement a regular preventative maintenance program for the UPS system. The preventative maintenance program should include inspections, testing, and cleaning. The preventative maintenance program should be based on the manufacturer's recommendations. Keep records of all preventative maintenance activities. Consider the potential for using an automatic transfer switch to switch between the UPS and the utility power. An automatic transfer switch can automatically switch between the UPS and the utility power in the event of a power outage or UPS failure. This can help to ensure that the critical loads remain operational during a power outage or UPS failure. Test the automatic transfer switch regularly to ensure that it is functioning properly. Document the results of the automatic transfer switch test. Consider the potential for using a generator as a backup power source for the UPS. A generator can provide long-term backup power in the event of a prolonged power outage. The generator should be sized appropriately for the load it is serving. Regularly test the generator to ensure that it is functioning properly. Maintain a supply of fuel for the generator. Implement a regular maintenance program for the generator. By taking these steps, the reliability and availability of the UPS system can be further enhanced. Also, check the power factor of the UPS system. Power factor is a measure of how efficiently electrical power is being used. A low power factor can result in increased energy losses and higher electricity bills. Correcting the power factor can improve the efficiency of the UPS system and reduce energy costs. The power factor can be corrected by adding capacitors to the electrical system. Work with the utility company to ensure that the power factor is within acceptable limits. Review the UPS system's warranty and service agreement. Be aware of the terms and conditions of the warranty and service agreement. Ensure that the UPS system is properly maintained in order to maintain the warranty coverage. Contact the UPS manufacturer or service provider for any questions or concerns about the warranty or service agreement. Investigate if the transformer feeding the switchboard is properly sized. An undersized transformer can cause voltage sags and other power quality problems. Ensure that the transformer is sized appropriately for the load it is serving. Consider the potential for upgrading the transformer to a larger size. Consider the potential for using a different type of transformer. Some types of transformers are more efficient than others. Consult with a qualified electrician to determine the best type of transformer for the application. Analyze the electrical load on the switchboard. Identify any loads that are contributing to the power quality problems. Consider the potential for relocating or removing these loads. Implement measures to reduce the harmonic distortion on the switchboard. Harmonic distortion can cause a variety of problems, including overheating of equipment and inaccurate meter readings. Harmonic filters can be used to reduce the harmonic distortion. Consult with a qualified electrician to determine the best way to reduce the harmonic distortion. Monitor the voltage levels on the switchboard. Voltage sags and swells can damage equipment and cause malfunctions. Ensure that the voltage levels are within acceptable limits. Install voltage regulators to maintain stable voltage levels. Investigate any grounding problems on the switchboard. Grounding problems can cause a variety of electrical problems. Ensure that the switchboard is properly grounded. Consult with a qualified electrician to inspect the grounding system. Implement a regular inspection program for the switchboard. The inspection program should include visual inspections, electrical testing, and thermal imaging. The inspection program should be based on the manufacturer's recommendations. Keep records of all inspections and maintenance activities. Consider the potential for using a power quality analyzer to monitor the electrical system. A power quality analyzer can provide detailed information about the voltage, current, harmonics, and other parameters of the electrical system. This information can be used to identify and diagnose power quality problems. Train personnel on how to use the power quality analyzer. Analyze the data from the power quality analyzer to identify and resolve power quality problems. Consult with a power quality expert for assistance with analyzing the data and resolving power quality problems. Consider implementing a power quality improvement program. A power quality improvement program can help to improve the reliability and efficiency of the electrical system. The power quality improvement program should include a power quality assessment, a power quality improvement plan, and a power quality monitoring system. Implement the power quality improvement plan. Monitor the results of the power quality improvement program. By taking these steps, the reliability and efficiency of the electrical system can be significantly improved. It's crucial to maintain accurate records of all measurements, tests, and maintenance activities related to the UPS and the electrical system. These records can be valuable for troubleshooting problems and planning future maintenance. The record should be stored in a safe and accessible location. The record should be updated regularly. Consider the potential for using a computerized maintenance management system, or CMMS, to manage the UPS and electrical system maintenance. A CMMS can help to automate the maintenance process and improve efficiency. Train personnel on how to use the CMMS. Regularly review the CMMS data to identify trends and plan future maintenance activities. And conduct regular safety audits of the UPS and electrical system. The safety audit should identify any potential safety hazards. Implement corrective actions to address any identified safety hazards. Document the results of the safety audits. Regularly review the safety audit results to identify trends and prevent future safety hazards. Safety should always be the top priority when working with electrical equipment. Ensure that all personnel are properly trained and qualified. Follow all safety procedures and regulations. Use appropriate personal protective equipment, or PPE. Never work on electrical equipment while it is energized unless absolutely necessary. Always to energize and lock out the equipment before working on it. Be aware of the potential hazards of electrical equipment, such as electric shock, arc flash, and fire. By following these safety precautions, you can help to prevent accidents and injuries.